Okay, so lecture 8, no, 9, sorry. Lecture 9, matrix transformations, and in this lecture we start some deeper ideas of, so let me try something. Okay, I need this. Some deeper ideas of linear algebra, and that is matrix transformations. Now, before I start, or I continue, let's say, I introduce some notation. You have seen these notations, but let's do it for once. So, let R be the set of real numbers, and I'm using this notation, which looks like epsilon. It means belongs to. R2 is the set of ordered pairs AB, such that A and B belong to R, and this is like the geometric, say, representation of R2. That is the XY plane, which you know from, say, I don't know, college algebra somewhere. Then it's R3, that is ordered with what we call 3 tuple. So that is the representation is the space XYZ space, and then it goes on R4, R5, and so on up to Rn in general, and this is like, and we call it Anton. Now, what do you know? Let's say you might have seen vectors in physics, maybe, or in Calc 3 or something, and usually vectors are denoted like an arrow or something, or let's say represented as an arrow. That's because in physics they, in fact, are used to model things which come with both magnitude and direction, like force, for example. But for us, and we will see in next chapter that how these two things, points in plane and forces that they use in physics, I mean that model they use in physics, are related. Well, in this picture you can see, at least in dimension 2, that this point AB and this vector OA, say, are kind of the same. So point AB gives me a vector OA, and vector OA gives me point AB. So, for us, we call these things vectors. And we call them vector spaces. Well, we will see what vector space is in chapter 3, in fact, the definition of vector space. But anyway, so for us, these are the spaces that we deal with. In these spaces, we can add vectors component-wise, and we can multiply each one of them by a constant. We can multiply this by k, ka, kb, kc, and so on. And yeah, that's it. Now, what we will do in this, say, course, or in most cases, not just here, we usually use column matrices to represent vectors. So a vector will be, you can either write it like this, A comma B, or A, B. Or here, this will be x1, x2, xn. Okay, so well, you have seen this thing. Well, like when I discussed the systems of linear equations, that was like a vector of unknowns, and you have seen like the right-hand side as a vector b1, b2, blah blah blah. Anyway, so let me start something else. No. But in mathematics, when you start studying some structure or some set, say, with some structure, maybe the second step they usually take is defining a relation between those structures. And that relation, one of them is a function. So if you are given two structures, say A and B, they might be just sets. You define a function from A to B. And that's what? That is, you assign arrows. So if I have, say, A here, this goes to, say, f of A in B. So this is A, this is B. And say A1, say this is A, f A1, A2 goes to f of A2, and A3 might go to f of A2 again, the same point. So the A, we call it domain, and the B, the book prefers codomain, not range for image or something. Okay, so now that we are dealing with these sets or these spaces, say, we have to define certain functions from these spaces, I mean, between these spaces. So, one thing which I should remind you that a function should be well defined. Which means when I say f of A is B, then I'm assigning B to A, right? And I'm not assigning anything else to A. So when I say f of A, immediately you think of B. You should think of B. Now in arrows, this means that this A goes to B. This is correct, but this A cannot go to another B. This is incorrect. That's not well defined. So when I say A, F applied to A, you should immediately say, yeah, that's B. Okay? You cannot say, well, maybe it is A, maybe it is B, maybe it is B prime, maybe it is blah, blah, blah. No. That is what we mean well defined. And that is, in fact, what you might have seen as a vertical line test. Remember the vertical line test? That was for graph of functions from R to R. So when a graph of function should be like this, which means if I have A here, then f of A, which is B, is unique. And that's when any vertical line that intersects the graph in one point. So if a graph goes down like this, then f of A is either this or this, B prime. Okay? So that is not graph of a function, and you know that from college algebra. So that vertical line test, in fact, is another way of saying that this should be well defined. Okay. So let's take a matrix n by n matrix. If I multiply A by a vector which has n, see this is n by n, and this is n by 1, so I will get something, a vector here b1 up to bm, right? m by 1. So it's like this matrix is doing something like this. This matrix takes a vector in Rm Rn, this is n, takes this vector into a vector in Rn. And it is well defined. When you multiply A by a vector like this, you will get a unique answer. Right? When you multiply, you will get a unique answer. So A, x, let's say this is x, and this is b. When you multiply A by x, you will get a unique answer. This b is unique. So you don't get two b's, b and b prime. So it seems that this a, in fact, is like a function. It takes, we can say that it takes a vector in Rn to a vector in Rm, and this vector in Rm is unique. So it's a function, but we can also, you might say, okay, no, this is a matrix what we're talking about. So we introduce a notation here. So we introduce a notation. Instead of using A, we use T sub A. Transformation defined by A. So transformation defined by A, this is not a function. So transformation defined by A is now a function from Rn into Rn. Now, at higher level, when there is no need to introduce that TA, many mathematicians just use A here. They say, okay, that A in fact is itself, they just take that to be that function. So they use the same notation for both of them. But let's use TA here, distinguish between a function and this. And this TA is defined, TA is defined as a function that takes x to ax. Okay? So this is defined as a function that takes x to a times x. Remember, a times x is a vector here. So it takes this x into a vector in the codomain. Okay? So, for this TA, which corresponds to this matrix AM by N, let me, so TA corresponds to this AM by N, and TA is a function from Rn to Rm. Now where do they come from, the M and N? Just look, this N in fact gives me the domain, this M gives me the codomain. Okay, this is the domain, and this is the codomain. So, TA corresponding to, say, this matrix, for example, 1, 2, 3, 4, 5, 6, 7, 8, 10. Remember the 7, 8, 9 was a very nice vector. So, well, let me add another one. So it's not 3 by 3. So let's add 10, 11, 12, 15, say. So this is 4 by 3, right? 4 by 3. This is the matrix A. And TA will be a function from R3 into R4. Okay, so this second one, the number of columns give me the domain, and the number of rows gives me the codomain. Okay, so now let me. So given a matrix, we can simply write. So given A, we have TA is defined as TA applied to x is AX. Okay. Now given TA, how to find A? No. Well, you might say, what do you mean by giving TA? Okay. So let me say TA, what was that, the R4 or R3? Into R4, right? That we had here was R3 into R4. So I should define TA as some function that takes a vector here in R3 into a vector in R4, right? So TA applied to some x, I should tell you what that thing is. So this thing should be a vector in R4, right? So this should be a vector in R4. So this thing should have 4 entries. So this thing should look like this. Well, let me draw it. So it should have 4 rows. In fact, each row has just one element or one entry because it is 4 by 1, right? This is a 4 by 1 matrix. And x is 3 by 1. You see here. If let me erase this and write 3 here and 4 here. So this will be 3 and that is 4. Let me erase. And so this will be, say, x1, x2, x3, and this should be something like this. B1, B2, B3, B4. Okay? So, let's just write some formulas on the fly. Well, here I have x1, x2, x3, so the first row I can say it is maybe 2x1 minus 3x2 plus 5x3. That's the B1. Then this can be minus x1, say, plus 10x2 minus x3, for example. The third row can be, say, 3x1 minus 2x3. There is no x2, okay? The last one might just be 5, no, not 5, let's say minus 8x3. Well, this one, 8x3, in fact means this, means 0x1 plus 0x2 minus 8x3, okay? So if you don't say the other two, or if you don't see some of the variables that come from the domain, it doesn't mean they're gone. No, they are there, but with coefficient 0. So, and at the beginning, when I find A, I usually write, sometimes even I do this at this stage because sometimes I make a mistake. So what I will do is just add this 0 times something inside this so I can see the matrix easily. So let me erase this. And so that is how, that's a function. That's a function, TA applied to x gives you that. Well, you can see that these are all degree 1. There is no degree 2. What is degree 2? Or degree more than 1? Or degree which is not 1. Let's say degree that is not 1. Or if I have some variables x1, x2, blah, 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 degree 1 is just xi. It's 1 here. If I have xi, xj, then the degree of this is 1 plus 1, 2. If I have xi squared xj 3, the degree is 2 plus 3. If I have 5, what's the degree of 5? X is 0, right? Well, each one of them might have some constant. 6 times this, 3 times this, minus 10 times this, okay? So this is 0. Degree is 0. The degree of 5 is 0. So every row of this thing, or every entry of this domain, image of this x includes the xi's with degree 1. Exactly degree 1. No degree 2, 3, blah, blah, and no degree 0. Degree 0 means just a constant. If I happen to have like a 5 here, this is not TA, this is not matrix transformation. This won't give you a matrix transformation. This gives you something else. So there shouldn't be constants. There shouldn't be any one of them squared or raised to any power. There shouldn't be any 2 of them or 3 of them multiplied. So no products, no exponents except 1, and no exponent 0, which is constants. Okay, so if I have this situation, then what I do is I usually complete this thing with, I just write the zeros. So I can write it here again with the zeros included. So the first one, there is no zero, so that's minus 3 x2 plus 5 x3. Second one is minus x1 plus 10 x2 minus x3. The third one is 3x1 plus 0 x2 minus 2 x3. The last one, 0 x1 plus 0 x2 minus 8 x3. Now the easiest way to write the matrix of this matrix transformation, which you see that this is, all of them are degree 1. There is no degree other than 1. I'm not saying more than 1, because degree 0 shouldn't be there too. No degree 0, no degree 2 and above. So I easily can write the matrix, just write the coefficients. 2, minus 3, 5. Minus 1, 10, minus 1. 3, 0, minus 2, and the last one is 0, 0, minus 8. This is the matrix A. And you can see if I have anything other than degree 1, then that goes nowhere, right? If I have x1, x2, where is it? This is for x1, this is for x2, this is for x3. What is x1, x2? Well, what is x squared, x1 squared, say? So that's how you write it. Just by looking at the transformation and completing the each row by adding the 0 terms, and then just write down the coefficients of the xi's, each row-wise here, and you have the matrix of that transformation. Okay, so another way to find this is using standard basis. So what is a standard basis? We will see what that is in chapter 3. Standard basis is EIs. Now, each one of them is a vector like this. So I have 0, 0, dot, dot, dot. There is a 1 here, 0, dot, 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 0. So the 1 is in ith row. So the 1 is in ith row. So E1, for example, is 1, 0, 0. In physics, they know this as I. E2, that's for R3. 0, 1, 0. In physics, they know this as J. And E3, which is 0, 0, 1. In physics, they call it K. So the EIs are for R3. This is for R3. For R3. These are in fact the IJK in R3. Okay. So if that's one way to write it. Now let's use the EIs. So another way is simply saying that A is a matrix like this. The first column is TA applied to E1. The second column is TA applied to E2. And the third column is TA applied to E3. Okay? That's another way. And remember, vectors are, for us, vectors from now on are column vectors, or column matrices. So let's apply this. So E1, what was E1? I erase that. So let me write the EIs here and try to find. So A will be let me erase this one. So TA applied to 1, 0, 0 will give me what? The first, these are all 0. So I will get 2 here, minus 1 here, 3 here, and 0 here. Right? Then TA applied to the second one, 0, 1, 0. You can see that each one of them extracts the coefficient of that column. This one will give me minus 3, 10, 0, 0. And TA applied to the third one, 0, 0, 1, will give me 5, minus 1, minus 2, minus 8. Okay? And these are, in fact, the columns of matrix A. And you can see these are, in fact, columns here. You can see that. And this is this. This one is this. And this one is this. So either way, now why this one is also important, because you might say, gee, I just look at the transformation and complete the transformation right on 0 terms, and that's it, I have the matrix. But in the theory, when you're like proving something, the transformation is not given to you. They just say there's a transformation TA. So this will be how you represent the columns of A. So you would say the first column will be TA applied to E1, then TA applied to E2, TA applied to E3. Okay? So you don't have to do this when you're given explicitly, when the transformation is given explicitly. Okay? So let me Now, the transformation really moves a point in its domain. So most often when we are given transformation in R2 or R3, we can visualize something. But transformation beyond that, R4 and so on, you cannot visualize anything. But well, let's just take R2. So if I have a transformation from R2 into R2, TA. Well, it moves points. So if I have a point here, A, B, or A, B, this point is moved somewhere. It becomes A prime, which is T, while I'm using A. Let's do something. Say A, not B, let's say point C. Then this is C prime, and this is TA applied to AB. Okay? So, for example, if TA is given by a matrix given by A, let's say it is 1, negative 2, say 3, or negative 5, something. So what does it do? So if I apply TA to point, say, 1, 0, then point 1, 0 will give me 1, 3. Okay, so this transformation does this. Takes, say, this point, which is 1, 0, to point 1, 3. 1, 1, 2, 3. So this is point 1, 3. This is 1, 0. What does it do to the other one? TA applied to 0, 1. That gives me minus 2, minus 5. So 0, 1 is this point. Where does it go? This goes to 1, 2. Oh, gee, this goes down here. 1, 2, 3, 4, 5. Comes here. So this point is TA applied to 0, 1. Right? So this is the C, this is the C prime, this is the D, and this is the D prime. So it does something to the whole space. Now this has applications, geometric applications. There are transformations like rotation, for example. Rotation is given by a very nice matrix which has sine and cosine. In three-dimensional also you have different rotations, and each one of them is given by a rotation matrix. So what it's doing, I don't know what this one is doing, because I just wrote some random matrix here, not random, but some numbers on the fly. But it's like this transformation is just, it takes like R2 and maybe stretches R2, maybe rotates R2, maybe shears R2, just like this, or things like that. So it basically does some, let's say, damage to this R2. But there are some things that this transformation, there's certain interesting things that happen. One of them is that the point 0, 0 doesn't change. TA applied to 0, 0 gives me 0, 0, right, in this case. This TA applied to 0, 0 will give me 0, 0. So if there is some function that moves the plane, like a translation, that is not a matrix transformation. It is something else. It's an affine transformation, what they call it. But anyway, so if it moves this, it's not in this category. So this transformation, a matrix transformation, should not move 0, 0. That's one way to check it. So if you check, you're given some transformation and you apply it to 0, 0 and you will get something else other than 0, 0, I mean the 0, 0 of the codomain. And you immediately say, no, this is not a matrix transformation. Now, another name for this thing is a linear transformation. We will see that in chapter 3. So that's one way to check and see if a function given to us is in fact a matrix transformation. And if you see it is not, then just throw it away. That is not matrix transformation. Maybe you can use it. It has some application, like if it is affine, then you use it for translations, for example. But anyway, it is not a matrix transformation. So that one way to check it is just check 0, 0. See where 0, 0 goes under this function. Okay, now. So let me write down some properties of this matrix transformations and so some properties. Let's TA is from Rm into Rm, and that corresponds to a matrix A, which is m by n. Remember, this comes here, m goes here. So, first of all, what is TA applied to 0? And this 0, remember, this is the n by 1, 0. This is A multiplied by 0, and that is 0. And this is the m by 1, 0. So this is in fact 0. So TA applied to 0 will give me 0. So this is number 1. So TA applied to k times some x. So this is A times kx. Remember, a matrix multiplied. This is a constant. The constant comes out. And this is k TA of x. So a constant or scalar comes, it's like it's coming out of the function. And 3 TA applied to two vectors, x1 plus x2, sum of two vectors, that is A times x1 plus x2. And you know how we can distribute this thing, ax1 plus ax2, and that equals the dream of every college algebra student. Well, I will come back to this. So, the same way you have TA x1 minus x2 is the TA of x1 minus TA of x2. Now, I said something about number, this is, well, I can say this is 3 prime because it's in fact, well, it's not like that, not 4 in fact, that's not anything but that 3. So I have to discuss this thing, and I said the dream of every college algebra student, and why is it so? Let's look at this. Well, let me erase all of them, except this one, and write it up there. Let me write it again up there. So that was this property, that this distributes over sum. So it seems that a matrix transformation distributes over sum of vectors or sum of elements of the domain. Now, I know every student at some point, even I have made this mistake, we say, right, when we are given ln or log, they say what is ln of a plus b, you might have made this mistake and you have written this as LNA plus LNB. So you have distributed, I have distributed this over addition. So I have distributed this function over addition, right? Distributed this function over addition. Wrong. Another one which I have seen students, they do that. So I have made this mistake, not this one. They write it as this. What is this? Well, let me write some other ones which you might have made that mistake. So A, sometimes when it is squared, you do that. You write it as A plus B. And one that I haven't seen happening too often is this one, the last one, and that is some students, this doesn't happen too often, but I have seen sometimes. Okay, and this is not equal. Now, what are these? Well, I haven't seen students distributing sine and cosine. It's interesting. So, what are these? These are, in this case, you are distributing the function f of x equals ln of x. You are distributing ln of x over some of, say, elements in its domain. What's this one? What's the function in this case? You are distributing the function x squared. You are distributing x squared over a sum. Here you are distributing the function square root of x. And here distributing 1 over x. We will see in chapter 3 that this property is crucial. In fact, when we define linear functions, a linear function has this property. It has another property, which was the second one in that list, and this one. But this is crucial in when we define a linear function. So the word linear is used. But students in college algebra, when they start studying algebra, they think linearly. Well, I do that, you do that, everybody. We love linear. When we walk, we try to go on a linear, on a line, not we go this way, that way, unless we are drunk. So we have the tendency to assume that a function is linear without knowing that. That's at least my opinion. So we distribute this over its components, or these numbers here, and also this one, and this one, and this one. Now, among all of them, there's no distribution here. You can't do anything, and also here, and also here. But this one can be distributed. In fact, what is the correct answer? The correct answer has plus 2ab. So this one is a squared plus b squared plus 2 times this times this. But this one, absolutely, this doesn't change. This one doesn't change, this one doesn't change. So we are distributing, students in college algebra the tendency to distribute the function that they study. And so let's see, what is the only linear function? What is the only linear function? What is the only function that is one variable function, single variable function that is a matrix transformation? Okay, let's find it. Let's find the only matrix transformation that exists from R to R. So we are trying to find TA from R1 into R1, right? So that's in fact R. R1 is R. And we know that a matrix transformation corresponds to a matrix. So TA corresponds to a matrix A. But this matrix A is 1 by 1. What is a 1 by 1 matrix? It's just something like this. Yeah. Well, that's okay. Something like that. Well, let's write K. So then we compute with this M. So it's just K, some constant. Okay, so the only matrix transformation from R to R comes from this matrix. So let's see what this matrix gives me. So what is TA applied to some number? This TA applied to some, say, X. That is matrix K times matrix X, that is Kx, right? Kx. So in a sense, TA X, we don't need the matrix notation for R1. In fact, it's Kx. Kx, like 2x, 5x or something, right? So that's just, and what is it? It's a line. I mean, its graph is a line, the simplest line, right? The simplest line. I will graph it here so you remember from algebra that is in fact Kx, right? What is the slope of this? It's K. That K is slope of this simple line. So the only matrix transformation in R1 is the simplest function, which is K times X for some K. And that's it. None of these functions, there's absolutely no other function from R to R that is a matrix transformation or a linear transformation or a linear function. That's the only one. So from now on, and in fact, this means what? This means that the K, this one, let me erase this. So this means that this TA applied to, say, X plus Y, say, it is TAX plus TAY, right? Well, that's so simple. This thing is K times X plus Y, which is KX plus KY, which is TAX plus TAY. So you don't really have to know that. You know that this constant distributes over those two. That's like basic when you start learning college algebra or arithmetic, whatever, I don't know. That is a property, among the first properties, that distribution of this over parentheses, right? So you just remove parentheses. So I can say never ever distribute any function, any single variable function. Never ever. You don't need to know this one because you distribute this automatically. You don't have to know that this is a linear function. So never ever do that. Never ever distribute any function from R1 to R1 or any single variable function. Anyway, so these are properties of matrix transformations and how to find the matrix A from the transformation and how to write transformation from the matrix. In fact, if the matrix is given to you, just multiply by x1, x2, blah, 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 and the right-hand side will be your transformation. So, and another thing which I should emphasize is this. So, if I have a matrix transformation, TA, which is like this, then what is a system of equations? System of linear equations. A system of linear equations is something like this. If this A corresponds to a transformation, so this is equivalent to this. TA x is B. So a system of equations is translated into this. It means find an x such that when this function is applied to x, you will get B. So in a sense, we are solving a matrix transformation equation. If matrix transformation is a function, we are solving a matrix transformation equation, right? So you can reduce it to just one equation. You can just talk about one equation rather than a system of linear equations. You can just say this is equivalent to this. And what else can we say? Well, that's what happens in mathematics. When you interpret something from a different standpoint, or when you define something and you relate this to something else, then studying linear transformations can help solving this, right? So if I study this TA, then maybe I find some results regarding the matrix transformations that can help me solve this AX faster, easier, or maybe it gives me another algorithm or a much better algorithm to solve a system of equations, which happens a lot. So that is how mathematics works. When you bring in some abstraction, that abstraction, in fact, can help understand this better, can help solve this better if that's an equation, and can help find a better algorithm to solve it using computer programming, and so on. So this is like the end of this chapter. There's nothing else in this chapter 1 of linear algebra, and next time I will start determinants, and I probably will finish it in one session. I'm not going to do everything in that chapter. It's just as much as needed in the other chapters, and then I will start chapter 3, 4, and so on. Okay, see you next time.